There have been many theories over the years about what makes a substance an acid. The Bronsted-Lowry definition that you use in A-level defines an acid as a species that donates a proton, that is, a hydrogen ion. Similarly, a base is defined as a proton acceptor. When an acidic molecule like HCl releases a hydrogen ion in aqueous solution, we say the molecule has dissociated. In Year 1, we learnt that strong acids like hydrochloric acid, sulfuric acid and nitric acid practically fully dissociate into ions when in aqueous solution, whereas carboxylic acids and phenols, which are weak acids, only partially dissociate into ions when in aqueous solution, and only release a fraction of their hydrogen ions, with the rest remaining bonded to the uncharged molecule. At this point we can develop the idea of hydrogen ions being released further. Hydrogen ions that are released will link up with water molecules by forming a dative covalent bond with the oxygen atom and form H3O plus ions. And so when we talk about hydrogen ions being released, we really mean the production of H3O plus ions. We can write out the equilibrium for when the weak acid, ethanoic acid, releases its hydrogen ions in aqueous solution. The acidic hydrogen ion from the carboxylic acid functional group is released, and the reaction is reversible, and the molecule can reform. The ethanoic acid molecule is releasing a proton, and so by definition is an acid. Let's look at what the water is doing. The water is accepting a proton, and so by definition is a base. Now let's consider the reverse reaction. The carboxylate ion is accepting a proton from the H3O plus ion to form the neutral ethanoic acid molecule, and as a result the carboxylate ion is acting as a base. The H3O plus ion is donating a proton, and so is an acid. If we compare the carboxylic acid, which is acting as an acid, with the carboxylate ion, which is acting as a base, we notice that these differ by a single proton, and as such are termed a conjugate acid-base pair. The water molecule, which is acting as a base, and the H3O plus ion, which is acting as an acid, also differ by just a single proton, and consequently these are also a conjugate acid-base pair. And so in this equilibrium we have two conjugate acid-base pairs. This equilibrium is often simplified as follows by leaving out the water and expressing the H3O plus concentration as just H plus concentration. The equilibrium constant for this equilibrium can then be written as follows, and such equilibrium constants are termed K subscript A. Ka is the acid dissociation constant. Ka is the measure of the strength of an acid, since the larger the value of Ka, the more the acid has dissociated into ions. Values of Ka for the various acids vary enormously in magnitude, from values that are greater than 1 for strong acids, to values in the order of 1 times 10 to the minus 10 for very weak acids like phenol. Often the term pKa is used to describe the strength of acids, and this then allows a scale that has a narrower range and is more convenient for comparing different acids than Ka values. The pKa is the negative of the log to the base 10 of the Ka. A strong acid can have a pKa as low as -7, whereas a weak acid like phenol has a pKa of 9.8, and many carboxylic acids have pKa's in the range of 4 to 5. To convert the pKa back to the Ka, we do the inverse operation, which involves changing the sign of the pKa and then taking 10 to the power of this value. Some acids have more than one acidic hydrogen that can be released in aqueous solution. Sulfuric acid, H2SO4 for example, has 2 acidic hydrogens, and as such have 2 equilibria to consider, and will have 2 Ka and 2 pKa values. Sulfuric acid is said to be dibasic. Acids with only a single acidic hydrogen, like hydrochloric acid, are said to be monobasic. Phosphoric acid has 3 acidic hydrogens and is termed tribasic.